Mainz is going to give a talk with title Comparison for Faltings'p-adic Simpson correspondence and the Scholze'sRiemann-Hilbert correspondence. Okay.
Yeah.
So please start.
Thanks, the organizer invited me here to give a talk. Today, I will introduce this work which joined with Kanzo. Okay. Firstly, I want to talk about the Simpson correspondence. Let X be a smooth complex projective variety. A Higgs bundle is defined to be a pair of vector bundle together with an endomorphism of this vector bundle with value in omega 1, which satisfies this integrable condition. And Higgs bundle is called stable if for every proper subshift F, which preserved by this Higgs field, then the slope of this subshift is strictly smaller than the slope of E.
That definition is wrong if your variety has dimension greater than 1.
Okay, we need to choose a very ample line bundle to define this.
No, that's not what I meant. I meant that in higher dimensions, you need to assume that the rank of F is smaller than the rank of E.
But this is,
You didn't assume that the sheaf is saturated and...
Okay, thank you. Maybe here I need somebody. Okay. Okay, yeah. Thank you for reminding this. And the Simpson's theorem says that there are homomorphisms between these three modular spaces. And the first one is the modular space of semi-stable Higgs bundle with trivial chain class. And the second is modular space for vector bundle with integrable connection. And the third one is the modular space of semi-simple representation of the fundamental group. Okay, now next I want to introduce Faltings'p Simpson correspondence in local version. Now, before this, I want to talk about the Faltings'p period ring. Let K be a p-adic field with residue field kappa. This W is defined to be the weight ring with coefficient in kappa. CP is defined to be the p-adic combination of an algebraic closure of this K. And A-inf is defined to be the weight ring of this project limit ring. The morphism in this project is defined by piece power. And we have a natural surjection map from A-inf to OCP. And this surjection map is, and the kernel of this surjective map is generated by a single element Xi. And this Xi is given in this form. And we can define B-inf just to add the inverse of P into A-inf. And this theta can be extended to a map, surjective map from B-inf to CP. And then we get the completion of B-inf with respect to the kernel of this theta. Because this theta is surjective to a field, and the kernel is generated by a single element. So this completion is just a discrete variation ring. And the maximum idea is generated by this Xi. And we can also define another element T, which also generates the maximum idea of this B-Down plus. But this Xi and this T, the p-adic variation of these two elements does not the same. Okay, and again, this periodic field there is a natural embedding map from this K to be drawn plus. Okay. Now, for the periodic locus, we let this U to be a small affine over OK. Which means this small means this R is just a tile over a Théorie model. For example, this R could be this ring. So this U is just a torus. Okay. First, we denote this R bar to be the integral closure of R in the maximal atelier cover of this generic fiber of U. And the A-inf is defined to be the weight ring with coefficient in this limit. And here the map between in this limit is also defined by piece power. And then we can denote this R bar hat to be the periodic combination of R bar. Similarly, we also have this theta surjective map, and the kernel is also generated by this single element. Then we define A2R to be A-inf modular Cauchy square. Of course, this is a first order thinking of R bar hat. Okay, this is the U. Now we can define the Higgs bundle in periodic locus. A Higgs bundle over this ROK bar hat is a pair where E is a finitely generated free ROK bar hat module. And theta is an endomorphism of E with value in omega multiple this Cauchy inverse. Okay, this Cauchy is just the kernel of the surjective map we gave before. And which satisfies this integrable condition. And a Higgs bundle is called small if this P alpha divides theta for some alpha greater than 1 over P minus 1. Okay, we denote this data to be the automorphic group of R over this ROK bar, which is also equal to the automorphism between these periodic combinations. A generalized representation of this data is a pair V rho, where V is a finitely generated free R bar hat module, and rho is a continuous semi-linear action of data on this module V. And a generalized representation is called small if V modular 2 alpha has a system of data invariant generators for some alpha greater than 1 over P minus 1. And we can also describe this generalized representation by continual Galois cohomology. For example, let this V be a generalized representation. First, we fix a base of this module V. And then for any data in this group, there will exist some linear map, linear endomorphism of V such that this rho data X on this space is equal to this linear map X on this space. So we can define this C data will form one cocycle. So this gives a class in this Galois, continuous Galois cohomology. And this generalized representation is small if and only if this class is equivalent to 0 modular 2 to alpha. Okay, this is for generalized representation. And now we can describe Faltings'p theorem in local version. There exists an equivalent functor from this category of small Higgs bundle to the category of small generalized permutations. Okay, we denote this functor by d at here. And this equivalent functor depends on the choice of several data. Okay, to describe this functor explicitly, we need to firstly introduce this data. Firstly, for this data R tilde, as we denote this A2OK defined to be A inf modular C square. And this, of course, this A2OK is a first order thinking of OK bar hat. So by the smoothness of this R, we can get a A2OK lifting R tilde of this ROK bar hat. Okay, this is R tilde, and then for the local delta tau, as we recall this A2R, which is also a first order thinking of R bar hat. So again, by this log smoothness, we can lifting this map, this natural embedding map from ROK bar hat to this R bar hat to a map from R tilde to this A2R. Okay, this is the local delta tau. For the local delta t and the t tilde, this t is just a local coordinate, and we denote this to be the associated derivations. And ti tilde to define to be a fixed lifting of this ti. Okay, this just t tilde is just consisted by this ti tilde. Once we have this local data, we can construct the Faltings'p functor as here. Let E theta be a small Higgs bundle. We define this the underlying module of a generalized permutation to be the underlying module of the Higgs bundle tensor with R bar hat. And since this theta behave like a connection, we can define an endomorphism beta tau prime from V to V for any two lifting. The endomorphism is defined by this formula. Okay, for any element in this automorphic group, this tau composed with delta, we will get another lifting tau. Now we can get the endomorphism beta tau and the delta composed with tau. If we compose this with the identity tensor with delta, then we get a delta semilinear map between V and V. Now we can define the semilinear action of delta on this V defined to be this composition. Then the Faltings'p functor is just send the small Higgs bundle to this generalized permutation. One can show this generalized permutation is small. Okay. Actually the functor defined here depends on this local delta, but there exists a natural isomorphism between this generalized permutation for different choice. And this isomorphism is given by a similar map as beta tau and tau prime. Okay. Now we can introduce Faltings'p-Simpson correspondence in global case. In global case, a global Higgs bundle is defined to be a vector bundle together with endomorphism of E with value in omega 1 multiple this C inverse, which satisfies the integral condition. And similarly, as local, we can define this small Higgs bundle. And here, the global generalized representation of this fundamental group is defined to be a compatible system of generalized representation on a cover of X by small affines. And the small means it is locally small. Okay, this is for Higgs bundle and generalized representation in global case. Now given the construction of a Faltings'p functor in global case, firstly, we need to choose a small affine covering of this X. And then we need to assume this X is A2OK liftable. And then we choose and fix lifting, this X tilde of X. By log smooth, so we get a log smooth lifting Ri tilde of Ri. And then we choose local data tau I, Ti, and Ti tilde as before for each I. Then we get local functors, we just denoted by Di, which depends on this choice of this local data. And by assemble these local functors, we can get the Faltings'p theorem in global case. For a liftable X, then there exists an equivalent functor from small Higgs bundle to small generalized representation. We still denote this functor by D at here. Okay, this is just the generalized representation just consists by these local ones. And the gluing automorphism is just given as before. Because for different choice of loaded data, there exists a canonical isomorphism. So we can use those isomorphisms to glue this one. Okay. We give a remark at here. This functor doesn't depend on the choice of this data, but it depends on the choice of the lifting of this, the lifting X tilde. If we choose another lifting, then we know that all lifting are forms of this H1X T1 theta torsion. So the difference is just an element in this cohomology group. And then for different choices, we get a different functor that they related by according to this community diagram. And the left-hand side map is just defined by twisting via this class C. Okay. Next, I want to introduce Scholze'sRiemann-Hilbert correspondence. First, I need to introduce this explorer and the period shifts over this site. For X to be a connected local notary scheme, this explorer and this site, roughly speaking, the object in the underlying category of this form, where the UI is a tau over X, and the UI from the map from UI to UJ are finite tau for sufficient large I and J. For example, for an open set U of X, we can define this U bar, which to be the limit of V run through over all finite eta cover of this U, which is an object in this explorer eta. And one has a natural projection nu from explorer eta to X eta. Okay, by using this natural projection, one can define this the structure sheaf OX and OX plus on this site. And by taking the periodic combination, we get O hat X plus and O hat X. Similar as before, we can define A inf, B inf, and also has a surjective map theta. And then again, we take the compilation with respect to this kernel, we get a beta round plus. And by added T inverse, we get the beta round. And here we define OB inf to be the OX tensor with B inf over this W. We view this W as a local constant sheaf over this site. And again, we have this surjective map, and we define this compilation with respect to the kernel, and define this orbiter. And here the OC is just defined to be the quotient orbiter plus modular this Kc. And one can define a filtration on orbiter and a connection on this orbiter. Okay. Now we can talk about the beta plus locus system, which is just a sheaf of beta plus modular that is locally on X pro alpha free of finite rank. O hat X plus locus system is a sheaf of O hat X plus module that is locally on X pro alpha free of finite rank. And filtered OX module with integral connection is a locally free OX module together with filtration and connection satisfy the Griffiths transversality. Okay. Okay. Now we can introduce Scholze's theorem, which says there exists a fully faithful functor from the category of filtered OX module with integral connection to beta plus locus system, which sends this E to this locus system defined in this way. And conversely, one can reconstruct this E with filtration and connection via this formula. Okay, this should be nu. Nu is just the map from X pro alpha to X alpha, the map. Okay. This is Scholze's theorem. Okay. Next, after we given the period sheaf, we can describe the generalized representation according via these sheaves. From now on, we take the X in this pro alpha to be the scheme XCP. And for any open subset of this X, we denote this U bar to be the project limit of V run over all finite alpha cover of UCP. And then this O hat X plus U bar is nothing just equal to the R bar hat. And O hat X U bar is just equal to R bar hat tensor with QP. Now we can, to give a generalized representation is nothing just O hat X plus locus system. Similarly, okay, now from now we will identify these two objects. Similarly, for the rational generalized representation, we can view it as an O hat X locus system. Okay. Now we raise a question. Let V lambda filtration be a filtered down bundle over XOCP. We have two ways to construct an O hat X locus system from this filtered down bundle. The first way is via the Faltings'p functor. Firstly, we take the grading Higgs bound twisted by this Kc inverse. And then taking Faltings'p functor, we get a generalized representation. And the tensor QP, we get an O hat X locus system. The second way is via this Scholze's functor. Firstly, we pull back to X pro eta via this nu, the map nu. Then we get a filtered OX module with connection. And then we take Scholze's functor, we get a beta plus locus system. Modular this C, then we get an O hat X locus system. The question is, does these two O hat X locus system coincide? Certainly the answer is no. We can see the Faltings'p functor depends on the choice of this lifting X tutor, but the Scholze's functor doesn't depend on any choice of lifting. So we need to choose a canonical lifting for Faltings'p functor. In general, there does exist some canonical one, but this canonical one does not be integral. So we need to slightly modify Faltings'p functor for this canonical non-integral lifting. Okay, now we introduce the canonical lifting. Firstly, as we talked before, this K can be embedded into beta plus. So we can also get a map from K to this A2OK 1 over P. And we choose a uniformizer of this K, which means the pi just generated the maximum idea of the OK. And then we get a subring A2OK pi, which is the smallest subring containing both OK and A2OK. And this A2OK pi is also a first order thinking of this OK hat, OK bar hat. And one can find some alpha 0 such that this A2OK pi is just equal to A2OK plus this OK bar hat multiple C over P alpha 0. And one also has a short exact sequence. We can see this, this is surjective and the kernel is just this module. Because this C is square 0 in this ring. So this is indeed a first order. This is indeed a first order synchrony. Okay, and this is for the subring. And then we can choose this canonical lifting R tutor. This R tutor is just defined to be the p-adic combination of this tensor product. And similarly as before, we can find a lifting tau, which from this R tutor to A2R add this pi. Okay, now in this case, for any two such lifting, the difference will contained in this module, because we can see it easily from this exact sequence at here. Okay. Next, okay, now we can describe the modified functor. A Higgs bundle is called very small if P alpha divides theta for some alpha greater than alpha 0 plus 1 over P minus 1. And a Higgs bundle over this generic fiber is called very small if it can be extended to a very small 1 over this XOCP. And if, for example, a graded Higgs bundle are very small. Okay. Now, now we can describe the modified functor. Let E theta be a very small Higgs bundle. We can define the generalized representation similar as before, except that here the beta tau prime is defined in this way. Because our theta is very small, this series is convergent. So we get this modified functor. But this is from the very small Higgs bundle, the category of very small Higgs bundle. We still denote this functor to be D. Okay, now we can introduce our main result. Let V lambda filtration be a filtered down bundle over this X. Then we define this E theta to be the graded Higgs bundle twisted by C. By using this modified functor, we get a generalized representation. And then, on the other hand, we can use we can pull back this onto X pro eta set. We can get an OX module with integral connection. Then we take a Scholze's functor, we get a B-down plus log system. Our main theorem says that the generalized representation coming from this modified functor and is coincided with the generalized representation from this Scholze's functor by defined by this M modular C M. Okay, this is our main theorem, which means that this modified functor is compatible with Scholze's functor. Okay, next I want to talk about a sublog system of L tensor OX hat. Let L be a ZP log system on the generic fiber of X. And then we can extend the coefficient to B down plus, then we get a B down plus log system over X pro eta. And then by using the null lower star and then take the null up star, we can get a filtered O hat X module with integral connection. And this connection is actually algebraic, which was proved by Diaolan, Liu Zhu, these 4 people. And V prime, M prime is the B-down plus log system attached to this E prime, which is a sub B-down log system of M. Now, so we can define the generalized representation by modular this C, and then we get this sub generalized representation of this L tensor O hat X. The question is, does this generalized representation comes from a sublog system of this L, which means that there exists some L prime such that this W just equal to L prime tensor this O hat X. Okay, we're trying to solve this question as following step. The first step, we try to prove this W comes from a CP representation of the geometric fundamental group. And the second step is we try to prove this W coming from a semi-linear CP representation of the arithmetic fundamental group. And the third step is the most difficult part, which we want to prove this W coming from a ZP representation of the arithmetic fundamental group. Up to now, we can prove the first step. For the second step, there is a necessary condition, is that this W must be Galois invariant. and we will give a condition. We will get a description of this when this W be Galois invariant in the last section. And for the third step, we don't up to now we don't know how, but we believe we need some forbidden structure to descend this coefficient from CP to this ZP. Okay. Now, for the first step, the result is this W indeed comes from a sub-CP representation. Okay, by our main theorem, first by our main theorem, we can show this Higgs bundle, the Higgs bundle attached to this generalized representation is semi-stable with trivial chain class. And then actually Faltings'p conjectured that all semi-stable Higgs bundle with trivial chain class correspond to general representation. But here we can't use Faltings'p conjecture. We need to prove this W come from genus representation directly. So our proposition give an evidence for Faltings'p conjecture. The key point of the proof is that the associated Higgs bundle of L modular P is trivializable under Faltings'p twist pullback. This is a key point of the proof. Okay, next I want to talk about the p-adic analog of this C-star action. First, we introduce the Galois action on generalized representation. Let V rho be a generalized representation. Let delta to be an element in this Galois group, and we choose a lifting delta hat of delta in the arithmetic fundamental group. And then the generalized representation V delta rho delta is just defined in this way. This V is just twisted, it's defined to be the V twisted by this delta. And rho delta is just defined to be the conjugation, then composed, twisted by this delta. Okay, this isomorphic class does not depend on this choice of this lifting. Okay, this is the Galois action on the generalized representation. Similarly, we can define the Galois action on Higgs bundle. The Higgs bundle, the underlying module, similar as before, is defined by this, the E twisted by this delta. Similarly, the Higgs field is defined in this way. A proposition is that under the modified Faltings'p functor, we have this equality, which means the modified Faltings'p functor is commute with the Galois action. In particular, the Galois invariant Higgs bundle will correspond to the Galois invariant generalized representation. Okay, this is the proposition. Next, I want to talk about the Galois invariant Higgs bundle, the relation between Galois invariant Higgs bundle and the graded Higgs bundle. Let E0 theta 0 be a very small Euro Higgs bundle. This Euro Higgs bundle means the Higgs field is an endomorphism of E0 with value in omega, without multiple that Cassey inverse. And then we denote this E to be E0 tensor with OX OCP. And the theta denote to be theta 0 multiple 1 over T. As we introduced before, this T and the Cassey both generates the maximum idea. So this 1/t is just equal to an element in a unit multiple the inverse of Kc. And then this Higgs bundle is graded if and only if the isomorphic class of the Higgs bundle is invariant under the Galois action. Okay, for the proof is easy because the Galois action on this E0 is trivial, and the Galois action on this theta 0 is also trivial. But the Galois action on this T is factored through the cyclotomic character. So for any theta, the action on this theta is just like a multiple number, a p-adic number. So this E theta is invariant means the E theta is isomorphic to E some constant multiple of this theta. And by the classic Simpson's argument, we can get this E theta is graded. Okay, and this proposition leads us to make the following conjecture. A Higgs bundle is Galois invariant if and only if it is graded and of form in this formula. Okay, this is a description when the Higgs bundle is Galois invariant. Okay, now let's recall Faltings'p conjecture. Okay, we have introduced this before. The Faltings'p conjecture says that a generalized representation is a genuine representation if and only if the corresponding Higgs bundle is semi-stable with trivial chain class. Together, this conjecture and our conjecture, we can get the equivalence between these two categories. The first one is Galois invariant genuine representation. And on right hand side is Higgs bundle, graded Higgs bundle, semi-stable with trivial chain class and of the form here. Okay. Next, we have two evidence for the conjecture. The first one is this proposition. The conjecture holds in rank 2 case, which means the rank 2 Higgs bundle is Galois invariant if and only if it is graded and of the form in that formula. And the second evidence is this proposition. All Galois invariant Higgs bundle is nilpotent. For the proof of this proposition, let E theta be a Galois invariant Higgs bundle, and E is invariant. Then, because this is Galois invariant, so its underlying bundle is also invariant. Then we get this bundle is defined over X, which means there exists some E0 such that this E equal to E0 tensor with this structure sheaf. Now, then after we have this equality, we can write this Higgs field as an element in this group. As this E theta is Galois invariant, so the conjugation class of this Higgs field is also invariant. And then we take the character polynomial of this Higgs field, then it is also Galois invariant. And as the coefficient is located in this group, where this k bar hat minus I is a theta twist. And on the other hand, we know this the Galois invariant of this part is just equal to 0 for I equals to 1 to R, because of this theta twist at here. So the coefficients are all equal to 0 except the leading term. So we get the E theta is nilpotent. Okay, thank you for your attention. I think.
So, okay, so yeah, thank you for your talk. So, any questions, please? No questions. Okay, so thank you again.